second senior here at Siena. I am specifically a math major here. Now, some of you might know me, and the other ones who don't would know that I love playing with stats and other fun little probability things. So when Nate brought forward this question for my research project, I kind of ate it up. The original problem was finding a $100 bill on the break room in the faculty office. The person and 4 coworkers, instead of doing something reasonable like going to the convenience store and getting 5 20s for it, or just pocketing it yourself and being greedy, decided, let's play a game. And so every player has a 1/3 chance to either pass to their left, pass to their right, or win the money. And the question was, what are the odds of the starting player winning? So we decided to approach this in a matrix format. And so we have A here, which is the passing matrix for the game. Now, to make it a little easier to understand, we also have this graph here to describe how the passing works. So you can see it is player 1, 2, 3, 4, 5, and the arrows represent the directions that they can pass. So there's the 1/3 to go to 2, and the 1/3 to go to 5 for player 1. And then you can see the other ones there. And that lines up with our matrix with row 1 having a 1 in column 2 and column 5. And then column 1 having number 2 and number 5 to represent that they can pass those locations. So Aij, using the coordinate idea where I is the row and j is the column, is the transition probability from player j to player I for the game. S here is the stopping matrix for the game. You can see that it is all just ones down the diagonal because you only win when you have the money. So this is a diagonal matrix. All of these are 1/3. That is why there's a 1/3 in front of this one. There was a 1/3 in front of the A as well to represent the 1/3 chance. So Sij is the probability of player J winning when the money is in front of player I. And because of the fact that it is a diagonal matrix, that only happens when I equals J. So we have the idea that A to the K, Ij, is the probability of passing from player J to player I in K overall steps. So therefore, the probability of the money starting in front of player J and player I winning after K number of passes would be S times A to the K. So the probability of starting in front of player J and I winning is the identity matrix the identity matrix times the starting matrix plus the starting matrix times the passing plus the starting matrix times the passing squared, and so on and so forth until however many steps we want. We want infinite. So using the geometric series for the power system we have here, we end up with S times I minus A inverse. This is because this one, when used, normally the R value has to be less than 1, and in this situation the spectral radius of A has to be less than 1 to make it converge. And we use inverse because with matrices you cannot actually divide, so this is kind of 1 over I minus A, but it's just inverse. You plugging in our matrices that we had and the numbers, we end up with this lovely thing where player 1, when they start with the money, has a 5 out of 11 chance of winning. You can also see that player 2, when they start, has the same probability. Player 3, player 4, player 5, they all have the same probability when they start of winning in 5 out of 11. And that makes sense. The original game, you have a 1/3 chance of winning off the spot. So clearly you're going to have a higher chance of winning than everyone else. And you can see the players who are the furthest away from our graph would be players 3 and 4. They only have a 1 out of 11 chance of winning. Clearly, it's not fair. And we can look at the table to make it a little more digestible to see. It's just not really fair for anyone. If it was fair, player 1's column would be all the same value. So, the question becomes, how do we make it fair? So we want to start small and build up our problem to the highest capacity we can. So we want to look at T of I as the chance, or the passing chance, that player I passes to the left or to the right. And we want to look at Wi as the probability of player I winning. So given that each player still has the 3 options, we want to keep that in mind. And so we want to look at how the winning chances relate to the probability chance. And so the winning chance is the absence of the probability chance in relation to 1. That's why when there are more than 2 players, we have Wi equals 1 minus 2 Ti. Well, when there are only 2 players, you can only pass to the other player. So it ends up being Wi equals 1 minus Ti. Using this idea, we came up with the hypothesis that if we define our Wi and Ti in this way, we can find values for them to make the games fair overall. So, our 2-player, skipping forward a lot to save some headache, we end up with this matrix here for each column and each row, where we only really want to take column 1, because that's the one we want fair, because that's the one that player 1 starts with. And you'll notice the 1 over I minus A in the brackets, that is the determinant. That is a singular value. You can divide by that. And that is a scalar multiplier, so it will only change the numbers at the end, and it makes them prettier than they could be. So we take row 1 and row 2, and we set them equal to each other. And that's how we get W1 equals W2 T1. And solving that down using the other properties we already had, we end up with W2 equals W1 over 1 minus W1. This equation innately has the property that W1 is positive between 0 and 1/2. If we go past 1/2, it becomes negative. So if we plug in the value of 1/3, which is in this gap, we end up with this table, where player 1 has 1/2 chance of winning, and player 2 has 1/2 chance of winning when player 1 starts with money. The game's fair. It's the same value. Now, if you look at the second column, you'll notice that player 2 has a 3/4 chance of winning. And that is because we had to make it a little fair. We had to buff up a probability of player 1 passing and nerf down the probability of player 2 passing, which increased the winning chance for player 2 overall. So with the equations, we ended up with a 3/4 chance of winning if they had started with the money. Moving on to 3 players, you may notice this matrix is a little more complex than the one before. There is a lot more there. So we will use rows 2 and 3 to start to solve this one. This is how we end up with this series of equations. And we find that T2 actually equals T3. And when you think about it, that kind of makes sense, because player 2 and player 3 are both the same distance away from player 1. So they would have most likely the same passing chance given their distance from player 1 if player 1 starts with the money, which is what we care for. So now we plug in for row 1 and row 2, and we end up finding that the passing chance for player 1 is equal to 1 minus T2 squared over 3 minus T2 minus 4T2 squared. Saving a lot of headache and a lot of extra math, that ends up with T2 having to fall between 0 and 1/2. We can plug in for 1/3 again, and we end up with T1 equals 4 out of 5, and T3, of course, equaling 1/3 because T2 and T3 are equal. And the table ends up looking like this. 1/3 all in column 1, showing that the game is fair when player 1 starts. And you'll see that player 2 and player 3 have swapped odds of winning, depending on who starts with the money, because of the fact that they had the same winning chance and the same passing chance. Now, unfortunately, the 4-player solution is even more work. In terms of the notebook, if I remember correctly, the 2-player solution took me about 1/4 to 1/2 of a page. The 3-player solution took me about a page, maybe 2 tops. The 4-player solution took me 4 pages in my notebook to get through, because these equations get big. So I only left a solution here. This was the solution I came up with when I finally found my numbers. You might notice that another 1/3 popped up, and that's because T2 and T4, who are the same distance away from player 1 in this situation, were equal. So we have that the passing chance for player 4 was 1/3, player 2 was 1/3, player 1 had a 5/12 chance to pass almost half the time, and then player 3 had 1/4 of the time that they were passing. And so you can see, column 1, all equal, game's fair, fantastic. Player 2, they have a 7 out of 15 chance, it's a little under half, but player 3 has a 13 out of 20 chance, because they have to have the highest chance of winning and the lowest chance of passing because they are the furthest from player 1. So, Unfortunately, we did not get to a 5-player solution before this presentation. And that is because, as I mentioned, the 4-player solution took me about 4 pages of my notebook. One equation of the 5-player solution took 4 pages of my notebook. So it got kind of messy quick. So for the future works I want to work on the 5-player solution, and I have even thought I might be crazy enough to try the 6. Because if I can notice a pattern, I would like to notice a pattern. And of course, here are my works cited. These are blog posts from 2016, but the original found use of Lucas numbers and the Fibonacci numbers for the solution in the original problem. That's just to confirm that we were right. But any questions? Yes?
What are the Fibonacci colors?
Numbers.
Numbers, yes.
Fibonacci has a sequence where it is the previous entry plus the previouser entry, so entry 1 plus entry 2 will equal entry 3, and so it's a recursive one. It goes 1, 1, 2, 5, 8 for the first couple numbers, so that's where the 1, 1, 2, 5 popped in for that problem.
Mm-hmm.
And the Lucas numbers, I'm not exactly sure on. I didn't really touch it much. They just said, these are the Lucas numbers, and I said, I guess those are the Lucas numbers. Any other questions?